Every year, about 50 meter-sized objects crash into the Earth's atmosphere. Now, these burn up and don't hit the ground, but still, we are in this cosmic shooting gallery. And that is the smallest ones. We know that there can be bigger ones, things like Chelyabinsk, 20-meter class, things like Tunguska, 50 meters across, that these objects are crashing into the Earth's atmosphere on a regular basis and can do some damage. And so astronomers have been working hard for decades now to try and categorize all of the objects that are out there. And in the last couple of years, astronomers have gotten really good at spotting objects within a couple of days before they actually strike the Earth, not only detecting them as they're moving through space, but actually predicting exactly the track that they're going to follow through the sky and even where the meteorites will land so they can be collected as samples. And now, the most powerful tool ever developed by humanity for this task is now online. Of course, I'm talking about Vera Rubin. Now, my guest today is Chow. He is a PhD student at the University of Washington at the Dirac Institute in their Department of Astronomy. And he wrote a paper about using Vera Rubin to detect asteroids within the last couple of days before they actually strike the Earth. And that, we know of 11 that have happened so far in the last couple of decades. And now it's expected that Vera Rubin will find 1 to 2 of these every single year. And this gives us an incredible opportunity to spot these asteroids before they hit the Earth, while they're burning up in the Earth's atmosphere. And then, of course, once they've rained down meteorite debris onto the surface of the Earth to be collected. So if you want to learn more about how Vera Rubin is going to help us find asteroids, enjoy this interview with Chow. At the time that we're recording, it's been almost a month now that astronomers have been able to work with Vera Rubin data, essentially live. How's that going?
It's been awesome. I think from, the very first alerts, which, as you said, were about a month ago, there's now been a huge amount of data pouring in from every night of observation on this telescope from
like
these
800,000 alerts.
That's right. Yeah, 800,000 alerts. And these alerts are basically any changes in the night sky, right? So these could be things ranging from stellar variability, so stars kind of, getting brighter and getting dimmer. This could be like supernovae. And then, for me, right, of course, the most interesting one are asteroids, right? Things that kind of appear once and then, might appear later in other images. And yeah, I think getting to work with that data has been incredible. Yeah, especially, considering that this telescope, LSST, has been like an ongoing project for 20 years, 20 plus years, and to finally see the first public alerts, to have that, to see the fruits of your labor after such a long time is, I'm sure, is awesome. I'm not someone who was there for the whole 20 years, but I was, I celebrated first alerts with a lot of people who were, and that was a really special, I think, moment.
So I've interviewed people about sort of various variable stars. Specifically, I talked to someone from Noir Lab from the Antares as their data broker. But this is a different field, right? These are asteroids, potentially comets, Planet 9. Mm-hmm. Is there a data broker that you like best for looking at this data?
Yeah, right now what we're using is Think. That's the data broker, I think, that the solar system folks who I work with and myself are mostly using. Yeah.
How's that spelled? Is it just F-I-N-K or
F-I-N-K? Yeah.
Yeah. Okay. All right. So if I just do a search for Vera Rubin Fink data broker, it'll probably come up.
That's
okay.
Right.
Great.
Yeah.
Excellent. And so, can you give a sense of just like what kind of volume is going through this? We talk about 800,000 alerts a night. Do we have a sense of how much of this is solar system based?
That's a good question. To be completely honest, I don't know.
Okay, no problem. Yeah. So let's talk about your work then. Your paper was that, that Vera Rubin can be used to search for asteroids that are on a collision course with Earth. And in fact, this is a thing now that astronomers have been doing for the last couple of years, right? Like we have seen, what you said, 11 objects before they hit us.
Yep.
So talk about this existing framework.
Yeah, so like as you mentioned, we've now seen 11 imminent impactors. These are asteroids that were discovered in space before impact with the Earth. So far, the first one of these was 2008 TC3, which impacted over Sudan in 2008, and since then we've seen 10 more. So most of these have actually come within the past few years. So seven, I think, of these 11 have been since 2022.
Mm, we're
There
getting
were
better.
two. That's right. We are getting better. There were two in 2022, I think one in 2023, and four in 2024. There were zero in 2025, which is a little bit unusual, but not too unexpected given the kind of that these are, kind of small number statistics, and these are pretty like kind of sporadic, like Poisson distributed events. Um, but yeah, we are getting better at this, and so the fact that we see like there's been such a big increase like recently, I think is really exciting because these are pretty rare events and that are expected to become more common, and these are important. Like it's important for a variety of reasons. I think from the science perspective, we're most interested in imminent impactors because this is an opportunity to characterize individual, NEOs, near Earth objects, as asteroids in space. You can point a telescope at it. You can look at its trajectory in space. You can get its pre-impact orbit. You can get, colors. You can get reflectance spectra at it from these objects in space. When they pass through the atmosphere as meteors, if you observe that, you can get some idea of what their strength and their physical structure is. If you look at, kind of how they ablate in the atmosphere, how they fragment in the atmosphere, you can get some idea of what their physical strength and structure are. If you, and then on the ground, if you can actually recover these things as meteorites, you can get even more data, right? You can actually just put it, in like a hydraulic press and see how much pressure it takes to crush it. You can look at the fine grained, the internal structure of it. You can do like a lot of isotope dating to see like what the age of this object is. So I think like the real science, that I'm really excited about for imminent impactors is being able to combine like kind of data from multiple different regimes in this in an interdisciplinary way that's not really something that's possible for a lot of other in a lot of other cases in astronomy.
Yeah, and I think about like each of those phases that you mentioned are tricky to observe on their own, that and provide tremendous science value. Like that asteroid that's inbound is just a day away or whatever, then they're very hard to spot. They're very faint, and yet there's really interesting sort of detecting how the gravity is pulling on it. You're learning a ton about its kind of composition and so on, and then catching them as they're burning up in the atmosphere. Like this is just people's door cams, not exquisite science instruments set out a night before ready to capture the entry of this object to get all of that spectra that you're going to see from it burning up. And then I know that the ones that crash onto the planet, that they get infected by Earth material
That's right,
almost instantly. And so a meteorite that's found within hours of when it falls is so much more valuable scientifically than one that has been there for years.
Right. Yeah. And to your point, like I think like so a lot of the science from these previous and I think part of I think the really exciting thing about imminent impactors that we found in our paper is that Rubin, because it goes so much deeper than a lot of these previous surveys that have found imminent impactors. So a few big ones, the Catalina Sky Survey, CSS, Atlas, the Asteroid Terrestrial Alert, Terrestrial Impact Last Alert System, Pan-STARRS. I don't even remember what that one stands for, but all these, like these kind of big, like all sky surveys that have found these asteroids before, these imminent impactors, have much less depth than Rubin, which is supposed to be, I think, go down to our RMAG 24. And part of that, that's amazing. And
the whole sky at magnitude 24.
At magnitude 24, yeah. Like that means that we're going to be able to see these imminent impactors much earlier. So, in our paper, we found that the the median discovery time of these imminent impactors was 1.5 days before impact, which is not a lot. It doesn't sound like a lot. But when you consider the fact that of the 11 previous imminent impactors, all of these were found less than a day before impact, you know, it's huge, right? And the fact is that the average, the median time for these objects these impactors that are going to be found by Rubin is 1.5 days. Some of these will be found, before that, days or even weeks before. And to your point, we've done a lot of amazing science already using just people's, Ring doorbells or like security cameras that have caught these meteors from these imminent impactors, like on video. Imagine what we could do with a week. We could set up, we could track precisely where it's going to hit, set up, set up exquisite, cameras and instruments to actually record every source of data that you could want for that, every wavelength, every kind of spectra. Like you could get every kind of spectra that you want from the meteor, and finally, of course, to picking up the fragments on the ground, right? Like, and the fact is that even nowadays, the trajectory determination for this has gotten pretty good. I mentioned this in the paper, but in 2023, the 2023 CX-1, which is one of these 11 previous imminent impactors, they were actually able to find the meteorite fall locations within a few hundred meters of where they predicted it. So that means that, yeah. So I think with more advanced warning than we had for CX-1, which was again less than a day, you could refine that trajectory a lot more and possibly just have people camp there, the night before, right, and pick up meteorites almost as soon as they fall, which I think is amazing that we were able to do that.
I don't know if you were around for the Tagish Lake meteorite, which was one that fell here in Canada, I think in Alberta, and
it's actually in northern British Columbia.
Oh, was it northern British? Okay, yeah, and that it fell, and it was in the middle of winter, and it fell on this lake. And the astronomers were like, please find this thing before spring, because it's the perfect environment. So someone took this thing and just threw it in the deep freeze for you. Then you just had to go and get your hands on it. And people were able to turn up the bits and pieces from it, which is incredible. So yeah, I can't even imagine. Like, do you think, give us a sense of just like the number. How many of these objects of this kind of size, in the meter-ish size, are striking the Earth every year?
Yeah, so about 35 to 40 meter size and larger objects strike the Earth every year.
Right. So a couple a month.
Yeah, a couple a month. Most of the, well, we had a couple just recently, right, with the Ohio meteor and then the one over Germany, right?
Yeah.
So yeah. So about 35 to 40 of these objects strike the Earth, per year. Most of these are going to happen over ocean. A lot of these are not going to be, of course, recorded. But if LSST can discover, even a couple of these a year, right, which is what we predict. We expect that LSST will discover 1 to 2 meter size and larger imminent impactors per year. That would more than double. I don't know if I should say more than double. That should around double, given there's so much uncertainty in terms of, like small number statistics. It should around double the current discovery rate of imminent impactors, of about, 1 to 2, which is also about 1 to 2 per year.
Right. Yeah. Yeah. And so, because, it's only able to see from the Southern Hemisphere, seeing the field of view that it has, and it takes about 3 days to kind of come back to its starting point. So I guess it had to have one of these rocks show up in one of the fields of view that it captured in that. So I can see why, day and a half is about how much time you've got of advance notice before this thing comes in. That'll be really interesting. So do we, are people able to start setting up and chase these? Is there a truck ready, an airplane ready to go with all of the instruments on board, and they can fly out and try to watch the meteor burn up as it's coming through the atmosphere?
That would be my dream.
Yeah. How would you do that? How would you set that up, do you think?
How would you set that up?
Yeah, what would be the way?
That's a good question. I think what you'd want to do is you'd want to have meteor cameras kind of set up around the world in as many, covering basically as much of the night sky as possible around the world, or the daytime sky. A lot of these fell during the daytime. And having, and just to maximize the chances that, you're already going to have something set up there by the time that you get notice that these objects are about to hit Earth. Besides that, I think that on short notice, one of the best things that to do is just like be prepared, right? Be prepared to fly out, to often to pretty remote places. You were talking about Tagish Lake earlier. My master supervisor actually led the recovery for Tagish Lake, and
there you
one
go.
and one of the things he mentioned was that like a lot of the people who went to northern BC to the Yukon to find meteorites from Tagish Lake were just like people like random like geology students in the department who were ready to go at a moment's notice.
Yeah. But I wonder, right? Like you get this trajectory, like how accurate is it that if you, well, like say with the 11 that have happened so far, and maybe the 1 to 2 per year that you're getting, how accurate can you be with this? Do you think that you can almost guarantee that if you were, say, flying an airplane on the right trajectory, that you would see it at the appointed time somewhere in your field of view?
That depends a lot on how precise the astrometry you're getting, not just from Rubin, but from all these other follow-up observations that are going to refine, like the trajectory. It depends pretty heavily on that. I think getting it down to the second would be quite hard, but I do think that, it is very possible to predict the trajectory quite precisely, even with, the existing systems that we have today. And whatever follow-up telescopes you have. So like, for example, like CX-1, right? The meteorite that the one of the imminent impactors that I was talking about earlier, the trajectory that they predicted based on, astrometry from telescopic observations, and the one they observed from the meteor in the atmosphere was within 18 meters of each other. So I think that,
Totally.
totally. Yeah. So the answer to that is, like, could you get at least set up, like, could you set up a tent, underneath where you expect it to impact and see it? The answer is absolutely yes.
Yeah, but that's not good enough. No, I want an airplane ready to go, fueled up on the tarmac, ready to go. That is a team just waiting, looking tough, sitting outside, packing all their gear, and then they get the call, and then boom, they've got, you can get anywhere on Earth within about 15, 18 hours. And so boom, you fly, and then you follow the track at the exact right time, and then and you're super high up, and then boom, you're watching this meteor come hurtling through the atmosphere, clear of the murk of the atmosphere. I think this is the way.
That's something that I think would be amazing.
Yeah.
And I think that what you described is possible.
Yeah, totally. Yeah. So, knowing about these last minute impactors is great, but these are harmless. These are adorable. These are 1 meter. What about some of the bigger ones? I know that we get hit by something that is more Chelyabinsk every 50 years or so, every 100 years. So how much notice do you think we get of the ones that are a little scary that you may want to not go near your windows when this thing is passing through your sky?
Yeah, that's a really good point. In our paper, we didn't talk specifically about larger objects. We mostly focused on these, these known kind of imminent impactors, roughly meter size. We did consider Chelyabinsk. LSST could not have seen Chelyabinsk because it approached from the direction of the sun, and so it's never, it's not going to point it towards the sun. But for a lot of these other, but we only considered kind of these smaller objects, as these are the ones that are most likely to hit Earth. I am also working actually with some other colleagues, working with a team at Duke University who kind of in a complementary work to ours have been looking at exactly your question, which is how much warning time would we get, and how many of these objects could LSST detect for larger objects, for Chelyabinsk-sized, 20-meter objects, for Tunguska-sized 50-meter objects. For 140-meter size, which are, those are the ones, that's the potentially hazardous asteroid limit that is defined by NASA, and that's the size regime that U.S. Congress directed NASA to find at least 90% of potentially hazardous asteroids in 2005. Yeah, and so I'm also working with them on this as well, and I think we found that LSST could discover about 80% of the 140 meter plus size asteroids, about 50% for 50 meters to 140 meters, about 25% for 20 to 50 meters. So these are Chelyabinsk to Tunguska sized, and then kind of between 10 and 20 meters, about 10%. So the overall, so for large impactors, for things that are in the potentially hazardous list, for things that are Tunguska sized and larger, the numbers are pretty good. For smaller Chelyabinsk sized objects, we're certainly not gonna see all of them, right? Empirically, we didn't see Chelyabinsk. I don't have the exact numbers on hand right now, but I believe that for the warning time we got for these objects was in simulations was on the order of weeks.
Yeah. Right. Weeks, which is great. I mean, weeks is not, the sky's on fire, right?
Yeah.
which is what you get for Chelyabinsk and Tunguska. Instead, It's weeks. This thing is going to fly overhead. It's probably going to take this track. There's going to be tons of follow-on observations. Let's everyone who's in this area be aware.
Yeah.
And I think that's really good.
Yeah, and like weeks, like to be clear, I guess, I guess maybe I wasn't like forceful enough, but like weeks is great because that's enough time to do tons of follow-up observations. That's enough time to warn people like, hey, this is a Chelyabinsk size object, a Tunguska size object is going to hit your city. It's enough time to do evacuations, like we do for hurricanes and other tropical storms, right? If you need to. Yeah.
Yep. So what's next then for your research?
Yeah. So one of the things that we talked about in our paper is not only on using the default 3-night LSST linking algorithm, as you mentioned. By default, LSST only considers an object discovered or linked if it is observed at least on 3 separate nights over a span of 15 days. That's a pretty stringent requirement for imminent impactors because a lot of these objects are pretty small and pretty faint. So often you might not get enough time to have LSST come back to that spot, like 3 times, right? By the time it's visible at all, it might impact in like a week, and that's not enough time. Might not be enough time for LSST to come back to it. So one of the things that we discussed in our paper and that I hope to implement is a 1-tracklet streak matching method. So currently the 3-tracklet paradigm for LSST exists because otherwise you'll have tons of false positives. You're going to completely overwhelm like the system with false positives, like fake asteroids that don't actually exist. But for objects that are moving very fast on the sky, and this is often going to include a lot of imminent impactors because by definition they're going to get really close to Earth. They're going to move they're going to move very, very quickly across the sky. If they move fast enough across the sky, they can actually streak. They can appear as an elongated streak.
Right, during that exposure.
During that exposure, that's right. And one of the things that I want to do is to implement a method that would actually match 2 of these streaks that are aligned, that have that are aligned, that have the right like on sky spacing, that have the right orientation as well. Because essentially, if you see 2 streaks aligned like this, that have the correct spacing, the correct orientation, the correct direction, it essentially eliminates, any chance of it being a false positive. And so what I want to do is basically develop and implement a method that's going to take these 2 streaks, link them, and then compute an orbit and a trajectory, and say, hey, this has a chance of impacting Earth. Let's follow it up.
Yeah, and not wait for the 3rd observation when it's too late.
Exactly.
Then you're at 9 days.
Right.
Yeah. But I guess theoretically, if it's moving fast enough, then it's going to move to a future field of view. Like depending on which direction Rubin is going, it's going to see it over here, and then it's going to come back to over here, and like there it is again, and then it's going to move along here. There it is again, and that's something that is moving quickly, and it has to be close to us to be able to be moving that quickly. But you could theoretically see that just from that streak in 2 images that would be enough for you to know if this is something that we should pay more attention to.
Yeah,
Right.
that's the hope,
But
right? In
one
that
is sort of like too many false positives.
yeah, one streak could be anything. It could be an asteroid. It could also be like a satellite. That's like a big factor. It could just
Mhm.
be like some, bug with the camera or something,
Right. Yeah.
but if there's two streaks and they're aligned, they have the right kind of, like length, that both of them have the right length. They're aligned in the correct way, right? Like, if you have one like this and one like this, obviously it's not the same thing, right? But if they're aligned in the same direction, if they're spaced, if they have the right spacing, because you have the length of the streak on the sky and you have the exposure time, so you have some idea of how fast its on sky motion is going to be, right? And so you can say, okay, if it's here, and then 30 minutes later in the next exposure it should be here, but we actually see it like way down here in another exposure. That's probably not a real asteroid. um you know so basically, the one tracklet method, the streak matching method, the idea with that is just like it's so much less likely to have like false positive, to be a false positive if it's streaking and if it's aligned and if they're, the orientation, the length, the directions all match precisely. Yeah.
Do you think there's enough bandwidth for the astronomers to do the follow-on observations? Like, is it, if you pull this off, would the number of detections go way up, but be less certain, and so it would require more observation time from people to do follow-on work? Like, every night you're you're proposing a new potential impact, or every 4 days, 5 days, that you'll keep the astronomers busy trying to do those follow-on observations.
Yeah, absolutely. So if we did implement this, and there absolutely there'd be a lot of candidates that we would be sending out to astronomers. And so one of the things that I want to do, that I'm hoping to do, is refine the algorithm, and the method as much as possible. So we're not, ideally we are not flooding alerts, for these other astronomers with like, we're not overwhelming them with too many candidates that are bad, right? That are never going to impact Earth at all. You're definitely right that a lot of these candidates are probably going to be followed up, and with some more refinement, we're going to know that they're not going to hit Earth. It's pretty hard to tell right now what's the kind of rate of these, like, trailed tracklets, that are potential impactors is going to be, just because, like, and it's really just because of the scale of Rubin. Like, Rubin will completely dwarf any other survey that has come before it. So we're really in uncharted territory here when it comes to just the sheer quantity of observations.
Is this the kind of thing that people with a pretty good telescope setup, like an amateur, can get involved in to do follow-on observations of this kind of thing?
Absolutely.
Yeah.
I think absolutely this is something that, like, an amateur, yeah, that an interested amateur with a good telescope could do follow up on.
Yeah.
Absolutely.
Yeah,
A
because
lot of
like, even
sorry,
like I've got the C star behind me, and it can do like
yeah.
15th magnitude. So,
Yeah.
I'm not sure, like, what kind of magnitude are these rocks at?
Yeah, so it's LSST obviously goes down to 24th,
Yeah.
and so a lot of these objects are going to be, detected by LSST when they're too faint for that. But a 15th magnitude telescope, a lot of these asteroids, um go below 15th magnitude a few hours or a day before impact. So this is absolutely something that I think an interested amateur could follow up on. I think a lot of previous imminent impactors have actually had like amateur observations, have actually had amateur observations.
And it's such a weird time. Like, it's funny. I was interviewing people from the Antares system,
Right.
and they're like, we don't even know yet what to do with this yet. Like, there's a fire hose of 800,000 alerts.
Right. Yeah.
Like, just like, you can write your own API connection into it. You can filter it for whatever it is that you want to see, but then it's going to have to be the grunt work for astronomers to look through, do follow-on observations, try and figure, like, all Vera Rubin is doing is saying, found it, right? And then it's everyone else to do all these follow-on observations to really get to the bottom of what a lot of this stuff is. And so it's all so fresh at this point that if there are motivated amateurs out there who have a reasonable telescope setup and they want to participate in these kinds of projects, there's there's tons of help that's needed, and you may be able to get to name an asteroid moments before it explodes into the Earth's atmosphere, right?
Absolutely, yeah,
Yeah,
absolutely. Like with 800,000 alerts, like you were saying, like there's no way that astronomers can go look, professional astronomers can go look at every single one of these and be like, this is interesting, this is interesting, this is interesting. There is a lot of space, with Antares, like you were saying, with Fink, with all these other solar system alert brokers and other things outside the solar system for amateurs to get involved. Yeah.
yeah, yeah. Knowing this much about the asteroids and the movement of asteroids, do you feel more confident? Do you feel safer, or do you feel, does it sort of bother you that there are this many chunks of rock flying right past our heads?
I would say I knowing more about it now than I used to, I feel safer. I
Good.
think
Yeah. Yeah.
I think knowing that, sure, there are 35 to 40, meter size and larger asteroids that impact the Earth every year, but most of them are going to be harmless, right? They're going to be like, the one that the Ohio meteor from a couple days ago, or the one in Germany, like last week. They're going to be awesome light shows to look at, right? And or if you're lucky enough to see one, to look up and be like, whoa, that was awesome. But they're not going to cause any serious damage. Something like Chelyabinsk, of course, like could. And I think that is certainly a risk that we have to prepare for, that we are trying to prepare for. But overall, I would say that, kind of having known more about, knowing more about asteroids and about, like Earth impactors, I feel a lot safer than I did when I was like, is a dinosaur killing asteroid gonna come wipe us out,
Yeah.
like tomorrow?
Yeah.
The
Yeah.
answer to that is no.
No, and like definitively no, that all of
Right.
the really big ones have been found. None of them
Yeah.
are nearby. Yeah.
Yeah. Mhm.
And what are you obsessed with right now?
Yeah. What am I obsessed with right now? So for one of the things that I really want to do is what you were saying earlier, is to actually observe one of these imminent impactors, you know, the first one that, hopefully, maybe the first one, could be the second one. Hopefully one of these at some point that Rubin is going to discover at some point during its 10-year duration. One of these imminent impactors is to see one in space as an asteroid, to do follow-up observations of it with another telescope, and then to observe that as a meteor in Earth's atmosphere, and then, as you said, to fly out to wherever it's going to land and go pick up meteorites on the ground. I think that would be awesome. That is something that I'm really hoping that I get to do sometime, yeah, in the future. I want to be on the plane heading to the meteorite
Looking out the
fall site.
window, chasing
Yeah,
the meteor as it's going through the atmosphere.
as
Yeah.
it's going through the atmosphere. Absolutely.
Yeah, that sounds great.
That's
Awesome.
that's what I'm currently obsessed with.
Wonderful. Well, good luck, Ian. I look
Yeah.
forward to hearing the results of your adventure.
Thank you. Yeah. Thanks for having me on the show.
I hope you enjoyed this interview with Ian Chow. I'll give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bela, Cooper Nelly, Darkfinger, David Gilton, David Matz, Evan.pro, Greg Feely, James Clark, Janice Smith, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smith, Michael Purcell, Nordspace, OneStepForAnimals.org, Brent Kaidu, Richard Williams, Sean Sargent, Stephen Fowler-Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So I hope you're enjoying my Vera Rubin series. And this is a great counter to the one that I did with the Noir Labs Antares system, which is more focused on deep sky objects, variable stars, supernova, gamma ray bursts, tidal disruptions, things like that. And now this group is more looking at the objects within the solar system, asteroids, comets, planet nines, things like that. And I really want to encourage you, especially as an amateur, someone with a telescope, someone who wants to get involved, that is now open season on asteroids, and that with a little bit of research, a little bit of programming skills, maybe partnering up with someone with programming skills, you can really participate and help out in both analyzing Vera Rubin data to be able to find these objects, as well as being able to do follow-on observations of these objects because there's like just never enough telescopes to be able to categorize their movements. And often you don't need a big setup. That with something that is under $1,000, you can participate in this kind of work and learn more about the sky. So I hope that this will encourage you to get involved. And I will continue to try and figure out how to make this more tangible, because I know still it feels all very theoretical right now. So I will do what I can to try and help you contribute to science and help you both discover things that are outside of our galaxy and stuff that's here inside the solar system. All right, we'll see you next time.